So we have previously discussed the dot product or the inner product or the scalar product, right? Where you can multiply two vectors and you generate a scalar. Today we're going to talk about the other multiplication style operation that you can do with two vectors, which is called the cross product. Okay, the cross product is represented by this sign, right? That kind of multiplication symbol. So the cross product has a couple of properties, and I'm just going to write them out. So the first property is that A cross B is going to be perpendicular to the plane containing vector A and B. Okay, so if I take vector A and take vector B and I cross them, then what I'm going to get is a vector that is perpendicular to both of them. Okay, and in fact, the plane that they lie on of necessity. 2, the magnitude of A cross B, and we'll look at this in a sec, is going to be equal to the magnitude of A times the magnitude of B times the sine of the angle between them. And finally, the direction of A cross B is given by the right-hand rule. The right-hand rule. So because this video does not, I'm not showing you my hands right now to do the right-hand rule, I'll probably try to post another video on right-hand rule that you can consult where I will actually show off my hands and do some right-handed rule stuff. But for now, just either consult that if it's up or go and find some other resources about the right-hand rule to determine kind of what direction a vector is going to point, right? Because I can generate two vectors that are perpendicular to the plane. One of them, if my plane is the xy plane, right? One in the positive z-hat direction, one in the negative z-hat direction. But which one is, well, we always choose right-handed coordinate systems, so it's always going to be given by the right-hand rule. Okay, so if I have a vector, let's say a vector A, and this is going to be magnitude A here, and I have another vector B of magnitude B, then one interesting thing about the cross product is if we use this idea here, if I make a parallelogram like this, and then I say, okay, well, let's find the area of the parallelogram. The area of the parallelogram, I can drop down an altitude, make it up. This is supposed to be perpendicular. And the height of this altitude is going to be equal to the magnitude of B times the sine of theta, right? So then if we just use the area of the parallelogram, because the base in this case would be magnitude A, right? Then I can find that the area of the parallelogram is going to be equal to the magnitude of A times the magnitude of B times the sine of the angle between them, theta. I forgot to label that, but this is theta. Which means that the area of the parallelogram is just going to be equal to the magnitude of A cross B. Okay, and we can also get the area of the triangle, right, which is half of the parallelogram, by simply doing half of this. So it's going to be equal to 1/2 the area of the parallelogram. Okay, so how do you actually compute cross products? Let's look at an example. So if I want to compute a cross product of two vectors, let's say my first vector is going to be A, and it's going to be equal to 3, 5, 7. And my second vector will be B, and B is going to be equal to 11, 2, 13. Okay, A cross B is going to be 3i hat plus 5j hat plus 7k hat crossed with 11i hat plus 2j hat plus 13k hat. And then we say, okay, well, now I have to FOIL this, right? And the way that you FOIL this with vectors like this is you multiply the scalars, so 3 times 11 is 33. And then you have to take the cross product of I hat cross I hat. Okay, so we have times I hat cross I hat. And then over here, right, we continue distributing. So I have plus 6 times I hat cross j hat. And then plus 39 times I hat cross k hat. And the way you do I hat cross j hat or j hat cross k hat, etc., is you have to do it with the right-hand rule. Okay? And that's the thing that I said, look up. For now, I'm just going to put up this handy-dandy chart. We have I hat, j hat, and k hat. We have I hat, j hat, k hat. And I'm going to write what all these cross products are. Note that what I'm writing in the boxes is I hat cross j hat. So this cross this. Because the cross product is anti-commutative, which means that A cross B is equal to negative B cross A. Okay? So if I cross two vectors that are in the same direction already, I hat cross I hat, that's just 0. If you go back to the magnitude definition, right, the sign of 0 is 0, so I'm going to get a 0 all across the diagonal here. I hat cross j hat with the right-hand rule is going to be k hat, which means we can also fill in j hat cross I hat, which is going to be the negative. And then I hat cross k hat is negative j hat, which means this is positive j hat. And then finally, this is going to be negative I hat and I hat. So we can kind of use this to do this out. So I'm going to have this, and then I'm going to do all of the rest. So I'm going to have plus 55. Oh man, yeah, these foiling out this long things. It's not fun. We're going to talk about a shorter way to do it momentarily. So this is j hat cross I hat. Just want to show you. You can always revert to this method as well. 5 times 2 is going to be 10 j hat cross j hat. Then we're going to have plus, we're going to have 65 j hat cross k hat. In the last row, you're going to have plus 77 k hat cross I hat plus 14 k hat cross j hat plus 91 times k hat cross k hat. Now, this, and this are all 0. And then for the rest, you're going to have to combine like terms. So you'll have to combine these two here, and these two here. Because these will give you the negatives of k cross j, right, is negative I, j cross k is positive I. So you'll subtract these two, subtract these two, subtract these two. In the end, what you should get, if you do all of your math very carefully, is 51 I hat plus 38, wow, I said 38, but we're 83, 38 j hat minus 49 k hat. Okay, and that's your cross product. Now, it would be a pain to do out this every single time you wanted to do a cross product, right? So there is an easier way to do it. And the easier way to do it is to simply say I hat, j hat, k hat, then write your two vectors here. So 3, 5, 7, 11, 2, 13. Take the determinant of this matrix. Okay, so you're making a matrix where this is your unit vectors, this is components of vector A, and these are the components of vector B. And if you do that, you're doing I hat times the determinant of 5, 7, 2, 3, 13, minus, don't forget the minus sign, j hat times the determinant of 3, 7, 11, 13, plus k hat times the determinant of 3, 5, 11, 2. Okay? And then you get the same thing as above. So that's pretty cool, and it's a much easier way to do it. Additionally, and I stick with the determinant method, I think, when you're kind of starting off, but eventually you can kind of shortcut it, right? Because you can identify which determinants are actually being done just in the vector itself, right? So if I have these two vectors, 3, 5, 7, and 11, 2, 13, right? Then what I'm actually doing is I'm crossing them and I'm getting something which is going to be my first component, right? Is going to be, we work from the bottom up. This minus that, right? And that's going to be my x component. So this goes here. This is going to look like a mess, I know. So I apologize in advance. I should really switch colors, but Let's see. Let's pick some colors. Grape. Then you're going to do this times this, or minus that, right? And then you're going to make it negative, right? So this one is going to go here, negative, and this one goes here. And just remember to put a negative sign in front of it. And then finally, you're going to do this times this. Just make it solid. And this is going to be your last component here. So you work from the bottom up when you're crossing the vectors, but then you put your solutions top down. And don't forget the negative sign here, because that's pretty important. Yeah, so that's another way that you can kind of shortcut dot products if you want to do it quickly. But be careful, and I would kind of get used to this way first, and then when you're feeling confident, you can do that. Okay, so let's look at a problem which has a use for cross products. Let's go back to, in our last video, we were talking about finding the equation of a plane. So let's find the equation of a plane that contains 3 points. Okay, so I have a point -5, 5, 5. I have another point, which is -3, 2, 7. And I have a third point, which is 1, 12, 6. How do I find the equation of a plane with 3 points? Yikes. We need a normal vector, right? I mean, I have my 3 points. I only need one of them. But I also need a normal vector. So how can I get a normal vector? Well, I know that one of the properties of the cross product is that if I cross 2 vectors, I generate a third vector which is perpendicular to them. So if I have my plane, what a crappy plane, and I have my 3 points, if I find this vector and I find this vector and I cross them, I get a normal vector, right? So let's do that. Let's find vector P1, P2. And if I find vector P1, P2, I'm going to get 2, -3, 2. And vector P1, P3, that's going to be equal to 6, 7, 1. And then I can cross these, right? So I can do my normal vector is going to be equal to P1, P2 crossed with P1, P3. And depending on which vectors you choose, you could get a different equation. You can test this, but it's fine that you can check that your equation is going to be just a scalar multiple of mine. You probably just going to be multiplied by -1. So for example, right, I could even multiply these in the opposite order. I would still get a normal vector, it would just point in the other direction. So I would just multiply my vector that I'm going to get by -1, and it would give me another normal vector, and that's fine. So if I do this cross product, right, I have I hat, J hat, K hat, 2, -3, 2, 6, 7, 1. So, feel free to pause the video here, try this yourself, make sure that you can do this determinant, though, you should have covered matrices, so I'm sure you can do this determinant. And you should find that your resultant vector is -17, 10, and 32. And that's our normal vector, okay? And now we want to plug in a point, and you can plug in any of these 3 points and you'll get the same answer. So I'm going to do -17 times -5 plus 10 times 5 plus 32 times 5 is equal to D. So that D is going to be equal to 295, which means that my actual planar equation is -17x plus 10y plus 32z equals 295. You might also see too, sometimes people will subtract the 295 from both sides and say you have all this stuff minus 295 equals 0. That's fine too. Either way of writing it is completely acceptable. So yeah. The last thing we have to do is, I don't know where that's actually it. So that's cross products. All done with cross products. So the key things to remember here, right? The key takeaways are that you generate a normal vector to the plane lying that A and B lie in if you cross A and B, and you can get the magnitude in accordance with the equation that we put up earlier. And it will generate a vector as a result, not a scalar. So cross product generates vectors, dot product generates scalars.